Okay, so let me get started. So our data basically comes from CERN and the Large Hadron Collider. So as you can see, the yellow circle, the huge yellow circle is the Large Hadron Collider. And the way it works is you have these two protons generally, you accelerate them in the collider and then you make them collide, hence the collider. And in this collision, like out of this collision, you get jets of particles. And the idea is we want to look for interesting phenomena in that, like in these collisions. And so as you can see here, there are 4 detectors along the way. So there's the CMS detector, the LHC-B, the Atlas, and the Alice. So these are 4 detectors inside which they basically detect what happens at these collision events, right? So this is what happens. So you have, in this case, you have 2 protons colliding, and they give rise to these jets of particles that then go and hit the detector. And so the detector basically will record what's the momentum of these particles, what's the energy of these particles, what angle is it hitting the detector at. And so that's basically what our data looks like, right? So one collision event is basically one data point. And so at these experiments now, you get data from these experiments, which is what you're actually seeing, right? But of course, there is a model, there's a theoretical model for what you expect to see from these events. So what we expect to see is basically given by the standard model of particle physics, which basically tells you with what probability do you expect to see what kind of particles at these sort of events. And now the idea is there's what we expect to see from the theoretical models, and then there's what we actually see, and if these two things actually match, or is there something that's unexplained in the actual data. So what we're looking for basically is evidence of beyond the standard model. So is there something in the data that is unexplained by the standard model that's beyond the standard model? And so in 2012, they actually statistically discovered the Higgs boson particle. So basically they had the model without the Higgs boson, and then they looked for, okay, so can we find evidence of something that will be supported by the Higgs boson model that's unexplained by the rest of the model. And so that's basically how they statistically detected the presence of the Higgs boson particle. So the idea now is that there are other theories that like there are other things that we think are there in the data that we can't explain so far. And so the idea is, can we find evidence of such things? So if you think about this data that I told you about, you can think of it coming as from 2 different processes. So the first process is the background process. So background here refers to anything that is explained by the standard model, right? And so in this case, the standard model sort of includes the Higgs boson particle. So it's basically anything that is explained by the current standard model as it stands. And signal represents anything that's basically, it could be an unknown particle, it could be an unknown interaction between particles. Anything that's unexplained by the standard model, we'll call it signal. Okay, so that's the background and the signal. And you can think of the actual data, the experimental data, as coming from a mixture of this background and signal, where the mixing proportion is lambda or it's the signal strength, right? And so no signal basically means lambda equals 0. And so let me see if this pointer works. Yep. So yeah, it works. So if you look at this PB, so this is the background density, and this is the signal density, and this is the density of the experimental data. And the idea is that if lambda is 0, you can think of it as Q equals PB, which is basically like a 2-sample test. So I'll come back to that again, but I'll show you how it is very similar to a 2-sample testing problem. So anyway, I skipped that too fast. So just to give you a toy 2-dimensional example, so obviously our data is not 2-dimensional, but just to demonstrate what the signal sort of looks like. So the red points here are the signal and the gray points are the background. And the idea is that each signal point on its own is not an anomaly, but the collection of it is an anomaly on top of the background. So each point itself doesn't stand out from the rest of the data, but there is this, the density changes at one location, which indicates the presence of the signal. Yeah, is there a question?
determines that these points somehow belong together, like close in time or like?
These are close in like sort of feature space. So they are close in sense of like what happens at those events are similar. What jets you get, what angles they're hitting at are similar. Yeah. So in this case, exactly as you said, so the signal is sort of a cluster of points. So it's almost like it's a small group of cluster of points which stands out anomalously on top of the background. Does that answer your question, sort of?
Just go ahead.
Okay, okay, we'll come back to it then. Okay, so that's basically what the problem is. And our objective is basically to detect this new physics signal using some sort of a collective anomaly detection algorithm. And what we are going to do is we'll do this in a model independent way. And here the model refers to the model for the signal. So do we assume something about what we are looking for? So are we looking for something specific versus are we looking just in general, right? So what we are going to do is we'll do it in a model independent fashion. So we won't assume anything about the signal. And finally, we use classifiers to build this test. And I'll go into more detail about how you can use classifiers to do this sort of a test. And the reason behind this is classifiers work really well in high dimensional space compared to like density estimation kind of a thing. So I'll come back to that again and we'll see what the difference is. And finally, I'll also talk a little bit about how we can interpret these classifiers. So how can we interpret these high dimensional classifiers and actually see what they are finding? So in that space, we're going to look at some active subspace methods, which will sort of characterize the signal that we find. And we also have a way to estimate the signal strength. So again, I'll go into all of this bit by bit through the talk. Any questions so far? Okay, perfect. Okay, so traditionally, how is this search done? So traditionally by physicists, this search is done in a model dependent fashion. So you generally assume the signal that you're looking for, and then you search for that particular signal. So in the case of Higgs boson, for example, they had a model for the Higgs boson, and they searched for that particular signal model, and they searched for that particular signal. And that's how they found it. But of late, basically, they realized that there are so many possible models that it's just not practical to test for all of these. And as a result, what also might end up happening is sometimes you may not even know what you're looking for. So you might find something that you don't really have a model for yet. So you need to leave the scope for that to happen. So initially, I'll mention how this works. So what you do is you have these background model and you have signal model. And since these models are super complicated, you basically have Monte Carlo simulations from these models. So you have a background sample that's generated from the background model and a signal sample that's generated from signal model. And these are labeled observations, right? And then you have the experimental data, which is background plus possible signal. You don't know if there's any signal. And so that's coming from this mixture density. And now the question is, in the experimental data, is there any signal or not? And this is unlabeled data, right? Because you don't really know what signals there and what backgrounds there. And so what they traditionally do is they train a classifier to separate the signal from the background. So train a classifier to separate the X's from the Y's. And then you apply this classifier to the experimental data to test for if there is any signal, right? But as I described before, the problem with model independent methods is, what if none of the current proposed methods is actually correct for the signal that's actually in the data? And secondly, what if you don't even know what you're looking for? In that case, how do you even have a model for it, right? So you could have something like this, which is a model misspecification problem, where you think that the signal is there on the top. And so you draw a classifier, but then it turns out that your actual signal is somewhere here, and then your classifier will not be able to find it, right? So this classifier is not going to have any power to detect this signal. So what do you do in such a situation, which is why we want to move away from the model signal model assumption. So what we do is we have the same things as before, except we drop the signal samples, right? So we drop the signal model assumption, we drop the signal samples, and instead what we do is we train a classifier to separate the experimental itself from the background. So instead of signal versus background, we train a classifier to do experimental versus background. And using this classifier, now we are going to test for whether there is any signal or not. So whether lambda is 0 or lambda is greater than 0. And as I explained, lambda is 0 is the same as the experimental data. So the density Q being the same as the density PB. So here, so this density will be equal to this density when lambda is 0. And so this becomes basically a two-sample testing problem, where you're looking for if these two samples, the background samples and the experimental samples, have the same distribution or not, right? So any questions so far? Yeah.
I have a set of questions for me, but let me ask you this one. So this is, so how reasonable is this? This is assuming that you have a clean sample of background, right?
Yes. So this does assume, so this will only find signal if the background simulations are a good simulation from the background model.
Right.
So yeah, I'll come back to this maybe towards the end, because
Yeah, sure.
This is a very interesting discussion, because it's like if you find something here, you probably have to do a more detailed analysis as to whether it's a problem with your background simulation itself, or did you actually find something. So this will be like the first step, and then you have to do further analysis. Okay. Okay, so now I'll explain quickly how we do this. So obviously, first we consider the likelihood ratio test. And so we are testing for lambda equals 0 versus lambda greater than 0. So let's just take the likelihood ratio on the experimental data. And so you can write the likelihood ratio as a function of the density ratio at each of the experimental points. And so what we do now is, like I said, we train a classifier to separate the experimental data from the background data. And the trick we are going to use now is, instead of estimating these two high dimensional densities and then estimating the ratio, instead we use the classifier itself to estimate directly the ratio instead of estimating the densities separately. Okay, so one problem would be to estimate Q separately, PB separately, and then take the ratio. But instead we use the classifier itself to estimate directly the density ratio. And the way we can do that is just using simple Bayes rule. If you're using a probabilistic classifier, you can write the classifier output as a function of the density ratio. And so you can just flip this to get the density ratio as a function of the classifier, and so you can estimate it, right? So this is simply a use of Bayes rule, where you can write it as the function of the Q over PB, and then you can find Q over PB as a function of the classifier. And so just using the classifier, you can estimate the likelihood ratio test statistic. Any questions here? I'll pause for a minute. Okay. You need a probabilistic classifier, yes. Okay. Okay, so the second thing we use is, instead of the likelihood ratio test statistic, we were like, what if we have this classifier, right? So what if we could use the performance of this classifier in some sense to measure if these two samples are the same or not? And so remember, under the null, these two samples have the same distribution, right? So a classifier that's trained to separate them shouldn't be able to find anything, because they have the same distribution. So there shouldn't be any difference between the two samples. So a good classifier should not be able to find any difference at all, right? So if you look at the ROC curve of the classifier, it should act as if it's a random classifier, correct? And if your classifier is actually a good classifier, it means there is some difference between these two samples that it's finding. So they're probably not from the same distribution. So using this idea of if the samples have the same distribution, it should be a random classifier. We came up with two other test statistics that you could use. So one is the area under the curve. And if it is a random classifier, from the left plot, you can see that the area under the curve should be 0.5, right? And if it is greater than 0.5, it means it's a good classifier. So there should be some difference between the samples. And similarly, you could also use the misclassification error, where under the null, if they are the same distribution, if it is a random classifier, the error should be 0.5. And otherwise, if it is a good classifier, the error should be small, right? So we also propose these two other test statistics that we can use to measure how different these two samples are. And we have asymptotic, bootstrap, and permutation methods to find basically the null distribution of all three of these test statistics. So I'll quickly go over a flow chart of how the thing works actually. So first, on the leftmost corner, you have the raw event data, and then it goes through this data cleaning and reduction process. So that part is done by physicists because we don't know what to do there. So that part is done by physicists, and then they give us these observations. So in our case, the experiments that I'll show you, the data is like 15-dimensional. And that's generally the dimensionality of the problem, like after the data cleaning process. It's about 15 to 20-dimensional data. So you have this data, which then you fit the probabilistic classifier to. And then with the classifier, on one side, you create the test statistic. So I haven't told you about the score test statistic because that's part of the model dependent methods. So I'll not go there. But we have the LRT, the AUC, and the MCE. And on the other hand, you also have to estimate the null distribution of these test statistics. And this we do using asymptotic, permutation, and bootstrap methods. And then finally, using this null distribution and the test statistic, you actually perform the test, right? And then you say whether you have found the signal or not. And on the other hand, using the classifier, we also do these interpretability techniques that I'll talk about soon, where we estimate the signal strength and find the active subspace to actually see what actually is the classifier finding, right? So that's going to be the other part of the talk. So the purple, the colored boxes are basically our contribution to this whole project. So especially the test statistics. So physicists generally just use the likelihood ratio test. So they haven't explored these other test statistics. So that is one of our biggest contributions to tell them that you could be doing these other things. And the other one is the null distribution. They're generally just taking the asymptotic distribution. And we actually see that the asymptotics are not great. So like just in our experiments, we see that the asymptotic methods do not actually work very well. And so the permutation and the bootstrap methods perform better. So it might be better to use these techniques. And finally, the interpretability also, like in the model independent framework, they don't really have any methods to do that. So those are basically our contributions. Yes.
What kind of classifiers are used in practice?
So I used, for our experiments, we use random forest classifier. They generally use neural networks. But yeah, you could use any classifier for this because the rest of it remains the same. You could technically use any special classifier you like.
Yeah.
So
yeah,
the permutation thing.
Yeah.
What exactly are we doing there?
So the permutation thing, what we do is because it's a 2-sample test,
Yeah.
so you can just permute the labels.
Okay.
So you can just put them in one bucket, change the background and experimental labels, and
Yeah.
compute the test statistic again and again.
And then you were using the test statistics that you mentioned here, the misclassification.
Yeah. You could use any of the three. So for each of the three, for each of the test statistics, we have all of these methods. So you'll basically have, so if you consider LRT, AUC, and MCE, and then if you consider these 3 methods, so you have like 9 different combinations basically. So technically in permutation, we have 2 different permutations. So it's like 4 into 3. But yeah, it's.
So but for the misclassification error then, what, I mean, wouldn't you just be interested in if it's just much smaller under the the real data and under the null.
Yeah,
That's really what we care about, right?
yeah.
So you were saying before, setting it equal to a half. But
So, I mean, you'll have to still construct it as a statistical test to see if it is like significantly different from a random classifier.
yeah, but wouldn't you just
So-
take all the null distribution values of the misclassification error and then take a look at the observed and see what quantile of the distribution?
Yeah, you can do that. But what we also could do is, so for the asymptotic one, you need the
Yeah,
null
then
value.
you need the-
Yeah. So the asymptotic one for the AUC and MC actually worked decently.
Okay.
We just use like we split the data into training and test sets and basically just use a Gaussian approximation and it works pretty well. But for the likelihood ratio, it doesn't work that well. Any other questions I can take? Okay. So I was just going to show the experiments now. So this is a data set that was provided by the Atlas detector, and it's available on the CERN open data portal. So this is the Higgs boson challenge. And so the idea there is that you have so the background model is without the Higgs boson, and then the signal model is you're looking for the Higgs boson. So in that case, what we did is we looked at what if you didn't know the model, and then the model dependent would be if you knew the model, right? So those would be the two different cases. And so you have the 15 variables. And as I said, these are like momentums, energy, angles at which the jets hit the detector. Those are basically your variables. And you have around 80,000 background and signal events. And what we do is we artificially create the experimental data in 50 different simulations. So we create it with varying signal strength. So we basically add lambda% of signal to the data to make it like an experimental data. So we artificially create the data to compare the power of the different methods to actually detect that signal, right? So this is the table that gives all the results, and there are lots of numbers. So we'll go over them bit by bit. So first we look at the first 3 of them. So these methods are the model dependent methods, right? So these are the ones that have access to the signal labels. They know what the true model is. They have access to the actual signal data. So we expect these to perform better, right? And then the bottom ones are the ones that are the model independent methods or R methods, which don't have any access to signal labels. So we don't really know what the signal looks like. But as you see from the power, so these are among like what percentage of the experiments finds the signal successfully. And the idea is you see that the power is comparable. So we are able to detect the signal almost as well as the model dependent ones, even though we don't have access to the signal labels. And here you also see that one of the permutation methods with the AUC is doing the best. And the reason this is important is because, as I said, physicists generally use LRT. So this is a good way to convince them to look at other test statistics as well. And also not just look at asymptotic tests, like look at bootstrap and permutation methods. So this is exactly the reason that we need to have these new methods. Yeah.
What's the asymptotic test that you say? Test?
So the AUC one, we use this approximation of its variance, and we just use standard normal as its asymptotic distribution. Yeah. And like I said, we split the data, so it works out pretty well. And
Did you try Wilcox test that?
we did not try Wilcox test. That's a good idea. I think there is. Because the variance, I think, is computed in a similar way. So yeah, I think it's similar. It's very similar. So yeah, so that, yes. Good question. So like I said, because we are splitting the data and so on, so even with the permutation and the bootstrap ones also, we split the data. So it works out pretty normal looking distributions, like the asymptotic distribution.
The assumption from how the background versus the signal.
Oh, the distributions of the background and signal itself, they are very complicated models, like, which is why we are getting simulated data from them. So
But are they kind of, because you had the example, ones were kind of a cluster, could be a normal, and the other one was.
so
only four.
people
Are they-
have used mixtures of normals to sort of approximate these,
Okay.
the background and the signal, but they haven't been very powerful above like 3 or 4 dimensional.
Yeah, I just wondered to what extent these tests would be.
So normals are not very bad.
Okay.
Like mixtures, like Gaussian mixture models are not very bad approximations. They are okay. But I guess fitting Gaussian mixture models itself is so
Yes.
difficult in higher dimensions. You're sort of losing power for that too. But I don't think they're very simple distributions.
And do you have a sense for what differences between the background and the signal make these tests stronger? Do you see what I mean?
Yeah, so it's not clear actually. I see what you mean, but it's not very clear why the classifier finds these things. But generally, like I said, it's generally a bump. And so what physicists actually do is they look at, so they don't do the search in a high dimensional space. They do the search in 1-dimensional or 2-dimensional spaces. And they look at these mass variables that are computed from the momentums and so on. And in one of the mass variables, I think they expect to see, like, so the background is sort of a smooth distribution, and the signal appears as a bump. And so one of the things you can think of doing is sort of do like a semi-parametric model, where you fit like a smooth one and then have a, yeah, so that's something people have worked on. And but in that case, you're sort of restricted to a lower dimensional space. You're no longer working in the higher dimensional space. So these ones are, they have the benefit that they're actually working in the higher dimensional space. But I think the idea here is like none of them is better than the others. It just depends on what you're looking for and what's actually in the data. So I think the idea is to use the whole spectrum of tests. So you would do like a model dependent test, see if you actually find what you're looking for, or you could do the model independent tests, and you could do the specific like 1-dimensional tests and so on. So it's a huge range of things you should be doing.
Just a quick question about, so you're only doing 50 experiments, obviously, so you're rounding your power to
Yes.
2%.
Yes.
If you ran 500 or 5,000,
Yeah.
would you be differentiating between the different approaches?
It's a good question. The problem is it's very computationally heavy because the data sets are huge. So, but all of the experiments we did, there were like smaller differences, but I don't know if they're like significantly different from each other. So yeah, it's unclear. Any other questions? Yes.
Just a quick, I guess, it's following from Joanna's question is,
Yeah.
do you see much difference in the signal picked up between like choices of classifier? So if you were to use like a neural net as opposed to a random
I'm
forest.
pretty sure you would.
Okay.
So there are specialized neural networks that physicists have designed to pick like specific kinds of signals.
Yeah.
So I'm sure the specific ones would be better than something you're just generally like a random forest classifier generally fitting.
Okay.
So which is why I think we intentionally want to leave the choice of the classifier to the user. Like if you know what kind of a thing it is and you want to fit a specific kind of classifier, then you probably should. Because as you can see, the power of the test is going to be dependent on the classifier. So
So in a sense, that's kind of where like a model could be seen to enter.
correct. So all of these would be sort of like, yeah, so you can sort of think of it as a weak dependence on the signal one, where these choices could be based on what you think might be there. Yeah, definitely true. So there's a range of, I think, methods that go from model independent to pseudo independent and so on. And it's all based on how weakly they are dependent on the signal model or even the background model actually. So like we were discussing, like if your background simulations are not great, then you're just going to find the difference between that. Like you just find the difference in the bad, like from the bad simulation to the actual data. So these are all very different things that like there's more research required. Okay, so now I'll show some experiments in the model misspecified case, which was this case, where the model dependent model is trained on that signal model, but it turns out your actual signal is this. So in that case, as we expect, the model dependent methods have no power at all to detect it because the signal has completely moved. So the classifier doesn't find it at all. Whereas in our case, we still have power because it's still like a signal, right? So we are still finding it. So it behaves exactly as expected. And then we did a couple more experiments. So if you look at this table, you see that the lowest we have gone to is 0.01 signal strength, right? So that's like 1% signal. And even in that case, we don't really have that much power. So one of the comments we got from the physicists was that generally the particle physics data sets that they are looking at has like much smaller signal strengths, like 10⁻³ -4 or something like that. And so the question is, how do you find those signal strengths, right? And what basically is restricting us from finding that small signal strengths is basically the sample size, right? So the bigger samples you have, the more signal you can detect. And the idea here is that particle physics data sets are actually huge. So they're like millions and billions of points. So the sample size is really not an issue in their case. And so we basically did a simulation to show that that's the case. So here we tried n is, if you look at the sample sizes on the right, so n here is the regular sample size from the previous experiments. And then we tried 10 times n, 20 times n, and 100 times n. And then as you can see here, firstly the power, so power is on the y-axis. So the power is increasing with n, which is expected. Like more samples you have, the more signal you have, the more signal you're training the model on. And so automatically like you have more power. And we see that even for like 5 × 10⁻³ we have power in this case with the 100 times sample size. So it's basically showing that as long as you have enough data, you will be able to find smaller signal strengths. So this is pretty realistic from the particle physics point of view. Like you could actually use this and find things in real data. Any questions so far? Yes.
What was the original n?
Pardon me?
What was the original n?
So the original n here was around 20,000. 40,000 actually. 2 × 20,000, 40,000.
Can you use simulations to calibrate the lambda? Let's say if you had a prior on it, depending on sample size, to be able to detect.
It's a good question. Yeah, I guess you could do that. So technically, actually, so I'm thinking how much detail to go into.
So the opposite of a power calculation to try to
Find the sample size you need, sort of a thing. Yeah, I guess you could do that, but yeah, theoretically, I'm just thinking if you can actually. The problem is that theoretically these classifiers are so hard to draw any sort of bounds for that if you were actually to create like bounds on the tests, like you would need conditions on the classifier, and those are like really hard to derive. So I'm not sure you could actually do that. Yeah, it's a good question. Okay, so now I'm going to move into the interpretability part of things. Are there any questions from the first part? Okay, have the time. Okay, so far, recollect that we have used this classifier, but the classifier is doing experimental versus background, right? So it doesn't really know where the signal is because it has this mixture of signal and background, and it has only the background, but it doesn't actually know how to recognize signal itself, right? And so now the question is, if your classifier finds something, or even if it doesn't find something, how do you know like what is it doing, right? So the question is, what are the relationships between the features that are actually influencing the classifier output? How is it deciding between the two classes? Or what are the differences between the two samples, in other words? So what we do, again, I'm going to demonstrate it just through a simple 2-dimensional toy example. Of course, our data doesn't look like this, but it's just easier to explain this way. So imagine you have something like the left plot where you have this uniform gray background, right? And then you have signal along these parallel diagonal lines, right? So now if you think about it, the direction that we're really interested in this example is this diagonal, right? Like perpendicular to the signal. That's the direction we are interested in, because if you look at that line basically describes where the signal actually is, right? So that's the line we are interested in. And so if you fit a classifier to this data, you'll get something like this. And the idea here is that if you look at this diagonal line, that's the line sort of along which the classifier surface is the most bumpy in some sense. So we'll basically try to find that direction. And the way we do that is you first look at the standardized gradients. So if you look at the standardized gradients, it will basically tell you how the classifier surface is changing in each of the variables, right? And then we perform principal component analysis on it. So this is PCA on the gradients. And what that tells you is the direction along which you have the most variance in the gradients. So what that's telling you is what's the direction along which your surface is changing the most or is the bumpiest, right? Okay. So those directions, so the PCA directions that we get, plus the mean gradient. So the mean of the gradients is basically along each variable is the classifier output overall increasing or overall decreasing is what the mean gradient will give you. So those are the things that are basically the most informative about the classifier surface. So let me again go through exactly how we find these things. So the standardized gradients, what we do is we fit a local linear smoother to the classifier surface. So we have these classifier outputs at these particular points. And then what you can do is you fit a local linear smoother to basically get smooth gradient estimates at each of the points. And then using these gradient estimates, you perform principal component analysis on this. And you could also perform sparse PCA if you wanted sparser eigenvectors. And then the eigenvectors are basically telling you the directions along which the surface changes the most, right? So that, along with the mean gradient, are basically capturing exactly what's happening to the classifier surface overall, right? So I'll quickly show you the results for the Higgs boson dataset to just show how to even interpret this, right? Like what you get from this. So the first plot you see here is the mean gradient computed on the experimental and background data. And so if you look at this variable, so what this says is as this variable increases, the chances of it being a signal increases, right? So the chances of it being like the classifier output increases for experimental data, and so the chances of being a signal actually increases. And similarly, if this variable is large, it again indicates the presence of signal. And what the eigenvectors tell you is a little bit different. So what the eigenvectors tell is these three variables together, when they increase in the same direction or decrease, meaning if they move in the same direction together, right? So if they all increase or if they all decrease, it indicates the presence of a signal. And similarly, in this case, these four variables, if they increase together or decrease together, it indicates the presence of a signal. And I know you can't see the variable names from here, but all four of these variables are basically phi variables, which is like this angle. And so it actually makes sense to physicists. Like this is actually finding something useful. So both these and then these three are, if you look here, they're like momentum variables. And again, like that makes sense. Like in the case of Higgs boson, this is actually giving useful information as to how Higgs boson is different from the rest of the data. So it gives useful information in this case, especially when you have something like a random forest classifier where you don't really know what it's doing, right? And the added advantage is that these methods are not just telling you which variable is important. So it's not really variable importance. It's more telling you what are the variable dependencies that are affecting the variable. So each of these variables on their own might not be important, but their combination or them moving together in the same direction is important. So they have to increase together. That is what's important for the signal, not if they individually change. So that's the beauty of this method, I would say. Any questions so far on this? Yes.
Yeah. So I think I was just because I was thinking exactly this, that they probably want to know which features are really causing the differences between the two sets, the simulated data and the experimental data. But I mean, do you have to be quite careful about how you're splitting your data up in order that you're not sort of using the data twice here? Because you kind of
You should not be using the data twice.
yeah. So you're using a different
Yeah.
So
your classifier is trained on the training data,
yeah.
And then you're doing all of these methods, including the test on the test data.
Okay.
That is very true, because if you do the training and the test on the same data, you end up with overfitting issues,
Yeah.
which will give you basically like just a peek at each of the points that you trained at.
Yeah.
So yeah, that's a problem.
So you're sort of using the training data to generate the hypothesis of which clusters of variables or features are, and then using the test data to find out.
Correct. So in this case, I think you can also think about this as the classifier now is kind of fixed, right? Because you have a classifier. That's the classifier you're trying to understand. So the classifier is already fit on the training data. That's done. And now using this classifier, you're trying to understand like what is the classifier doing? And so you use a completely different set of data to actually do that. Yeah. And the error intervals here are just like bootstrap standard errors. So that's how we're finding the error bars. So the last part of my talk is going to be the signal strength estimation. So like I said, again, the problem here is that you don't really know what the signal is, right? So how do you know how much signal is there in the data? Because you're not identifying the signal points. So how exactly do you know how much signal is actually present in the data? So the problem is that you have a classifier that's separating like the background data, which comes from PB, from a mixture of PB and PS, right? So you don't really know what the mixing proportion is, and you can't really estimate it in a very simple fashion. So what we found was, if you consider this weird transformation called the Neyman-Pearson quantile transformation, and I'm not going to get into how we went into this transformation, but the cool thing is, if you consider this transformation, and if you apply it on the experimental data, so if you take the W's, which are the experimental data, you apply this quantile transformation on it, and you consider the density of it, it turns out that lambda is just the density evaluated at 1. And so 1 here is a boundary point, because as you can see, the transformation is between 0 and 1. So you're transforming the data to the interval 0, 1. And if you compute the density of this transformed data at 1, you get it as lambda. Okay. And so now the simple thing to estimate lambda is you just estimate this density, right? But the problem, the only small problem here is that you're estimating the density at a boundary point. So it causes some challenges, but so I'll go into how we actually estimate that. So before that, this probability itself also is something that we don't know, right? Because PB is like the background model is really complicated. So we also have to estimate that. So we are estimating the transformation at each experimental point. And so using these estimates, we'll now find the density, like estimate the density, and then compute the density at the boundary point 1. So now what happens is the density GQ is actually a monotonically like decreasing function. And again, I'm not going into the detail of why, but it basically has to do with that it's a quantile transformation. So it works out that it's a decreasing function. So what we do is we just create histograms first, and then we fit a Poisson regression model. So this is count data, right? So which is why we use a Poisson regression model. And you fit a Poisson regression model beyond a threshold to basically get this edge point. And so we also used like kernel density estimation at boundary points and compared it to this. And surprisingly, like something as simple as this fits better than kernel density, because kernel density is not able to use the information that it's a monotonically decreasing function. Whereas in this case, you're just fitting a line. And so it's easier to describe that decreasing function. So it surprisingly works pretty well. And so we have these sort of like, we just fit the regression on the tail. So how you decide on the tail versus how many bins you make for the histogram, that obviously changes the estimation process. And we basically, for all of these methods, we have sort of bootstrap standard error bars and estimates. But this is just to give an idea of how much the signal strength is. Now, this is not so powerful that you create a confidence interval from this and perform the test of whether lambda is 0 or not. So our tests are more powerful than this. But this at least gives you an idea of what could be the value of lambda. So that's the purpose of this. So I'll just summarize quickly. So what we did so far is I showed you how you can search for new physics signal using this sort of a collective anomaly detection algorithm. And we are detecting this signal in a model independent way. What we do is we use these classifiers to basically find difference between experimental data and background data. And we use test statistics, which are functions of this classifier output. And so the test statistics we used were the LRT, AUC, and the MCE. And we also saw that the AUC and the MCE perform better than the LRT, which is something that we want to pass on to the physicists so that they start considering other possible test statistics for the other tests as well. And finally, we use the asymptotic bootstrap and permutation methods to estimate the null distribution. And I showed you how we came up with the active subspace method, which can characterize what are the variables important, possibly important for the signal. And finally, we did the signal strength estimation as well. So that was basically all of it. And you can find the paper on arXiv. And right now, that's my email ID, but it's probably going to change soon. But I'll have access to the email ID. So send me questions on that. Just stop at this.